our next speaker is Kolya Larson from the Ohio State University. I'm a PhD grad from there, so I have to say the. She'll be talking about broadband optical infrared variability in quasar spectral energy distributions. So take it away.
Okay, hi, I'm Kolya Larson, and I'm a third-year undergraduate astrophysics major at The Ohio State University. And this summer, I've been working with my professor, Don Turndrup, along with his collaborators, Joseph Choi and Karen Laley. As it's been known, quasars are variable, and now we're looking at their variability for quasars that are part of our large spectroscopic surveys. This is linked to Sophia Pasquini and Joseph Choi's talk from just a little bit ago. When studying spectral energy distributions in line absorption and BAL quasars, many issues can arise through these analyses. For example, quasars have temporal variability from small to large scales. Because of this, we may be assembling photometry and spectroscopy that was in a different state at earlier times, or different state at different times, sorry. We want to take a look at variability so we can identify quasars for which this may be an issue. Another difficulty is that certain catalogs, such as 2MASS, didn't detect many of the fainter quasars that our group is studying. If they were detected, they had large errors in the photometry. This is an issue because we need the J, H, and K bands from 2MASS to do the spectral energy distribution models correctly. Because of these issues, we need to explore deeper into understanding different kinds of variability in our quasar samples, which will allow us to create better spectral energy distribution models. Mostly, we've been using catalog data for our analyses, but we've also been getting new optical and infrared photometry from APO and MDM. This can help make up for missing pieces from the 2MASS and other catalogs, and show if our quasars have varied since the previous catalog data was taken. So over the summer, I created a program in Python that will allow for easy analysis of large samples. I'll show you some examples of variability plotted through this program using samples of photometry taken from the Zwicky Transit Facility, or ZTF. ZTF has relatively high cadence, recording data many times per season, hence why it would be a useful source. Here's an example of an output, Markarian 486. It is a nearby and bright quasar with a redshift of only 0.039. On the x-axis, we can see time in days, and on the y are magnitudes in G and R respectively, with brighter towards the top. We can see that it is obviously variable versus time, changing by 0.3 of a G-band magnitude in just 200 days. The formal error bars are smaller than the points themselves, but you can see that points are more scattered on short timescales. If you interpret the error bars to be correct, the quasar would have extreme variations on very short timescales. This seems unlikely, and it is more likely that these error bars are underestimated. Although the variability is obvious here, for less variable objects, it will be important to understand their true errors in order to identify if they're actually variable. Another problem you may have noticed are the stray points that are obviously incorrect. These points can skew the data, making the object look more variable than it really is. An automated procedure that does not filter out these stray points will overestimate the variability. We also see other systematic errors in ZTF. Stars that shouldn't be variable seem to have slight variation with time. This does, however, suggest that we can correct quasar photometry by comparing our quasars to their nearby stars. Here's an example of a more typical quasar in our survey, J1723 plus 5553. This quasar is further with a redshift of 2.112. It is also much fainter than Markarian 486, especially in the G-band, with average magnitudes near 20. These graphs shown have the same format as shown on Markarian 486's graphs. The large error bars shown in G make analyzing J1723 plus 5553's variability more difficult. Is there even variability at all? Meanwhile, in R, the error bars are much too small, like Markarian 486's. Also like Markarian 486, there are also stray points that show up across all of the bands. These problems in the ZTF data all contribute to difficulty in variable analysis. This season, we took G, R, I, and Z magnitudes for J1723 plus 5553. These were taken on MDM's 1.3 meter telescope. Here's a plot of G, R, and I data from ZTF. These G and R are the same plots as shown before, including our new MDM data, which is the red point. It looks like the quasar got a bit brighter in G than it used to be. Variability is expected to be different at different wavelengths because the light comes from different components of the quasar, such as its accretion disk or its dusty torus. Also, changes in deep bows could alter the broadband photometry. Our MDM errors are only 1 to 2%, so they're pretty accurate. Since we can get errors this small, gathering more data from MDM will prove useful. We should gather this data in as many filters as possible to find such variability. We also took infrared photometry from APOSS 3.5 meter telescope. One quasar we looked at was J1556 plus 3517. This is a bright quasar with a redshift of about 1.5 and lots of nearby stars on its field. Here we can see two graphs of this quasar's magnitude versus nearby stars' magnitudes. The horizontal axis shows the two mass data for these objects' magnitudes in H and K respectively, and the vertical axis shows our APO measurement in these same bands after calibration. The red point shows the quasar. It's brightened slightly in K since the two mass data. We chose this quasar because it shows the best possible case, a bright quasar that's surrounded by many stars. Especially in K, the calibration requires large color terms. The K filter in APO is not a perfect match to 2 masses K. 2 mass only goes down to about 16th magnitude in J, H, and K. We can get 10% errors 2 magnitudes fainter than 2 mass. Here we can see the images for J1556 plus 3517. On the left, we see the 2 mass image, and on the right is the APO image. As we can see, the 2 mass image shows way fewer objects than APO does. APO allows us to see fainter objects than just the 2 mass catalog would. Now that we found these problems in ZTF survey data and catalog data, what are the next steps we should take? Well, for one, we will continue to develop tools for quasar selection in future studies. Our goal is to get contemporaneous photometry when we obtain spectra at Gemini, APO, or LBT. We also hope to improve calibration methods for APO and MDM images, specifically when nearby stars are faint or the quasars are in sparse fields. Thank you for listening.
Very nice talk. Thank you very much. Do we have any questions up there? Don't be shy. Yes, Nancy.
So I'll ask a question. That was a really nice talk. Thank you. And I really enjoyed this whole series of talks so far because I've learned a lot. You know, you were saying sort of at the beginning portion of your talk that the very short-term variability is pretty unlikely. And so you're, you know, sort of trying to further investigate the sources of uncertainty in your photometry. But are there, I mean, can you think of any explanations? Like if the uncertainty were, I mean, if the variability were real, could you think of any physical explanations that could cause that? Or is there really nothing that could do that and therefore you're looking at other options?
Okay, so I'm pretty new to this because I'm just an undergrad, but like as far as I've been told, just like the physics of the quasars would not be letting that happen on like such short time scales. And so suddenly, you know, changing like that. So I don't really think that there's an explanation other than an issue in the actual data itself. But I mean, maybe somebody else here has an answer.
Well, I think you were saying that, you know, that the variability, at least for some of those plots, was much bigger in anticipated errors. And it certainly looked like you had some smooth curves there, which you can only get if your errors are not that big. So don't underestimate yourself. I think those look pretty good. Any other questions? I guess I had one about your sample. How are you picking these quasars, and how big is your sample?
Well, our sample keeps expanding. I'm not entirely sure how we decide how we pick them. I don't know, maybe Dr. Turnjob or Karen Laley can answer that for me.
So I'll just say something short. So it's kind of it's a process, right? So we started with the low redshift FE low balls because they're sort of simple, and then going to higher redshift stuff like Sophia showed brings in some more complications that we're not quite ready for yet. Ultimately, we plan to do sort of a cross the redshift board kind of thing. And there's some other stuff, there's some other objects that left over from back when we were looking at metastable helium. You remember metastable helium. Yeah, so it's a motley group of quasars.
All right, motley crew. Well, that was a nice talk. I